So, like I said, it just feels backwards because instead of doing the math first and then answering questions, we got the equation from our graphing calculator and then we worked backwards from there. But that's how this problem had to be done. So we put all of our data in there, and then we went to stats, calculate, quadratic regression, and I've got the old one, so I have to put L sub 1, comma, L sub 2, comma, variables, y variables, boom, boom, there it is. And turn on my stat plots again. I wonder if my window is set. Yep, my window was set for a different problem. So I'm getting all this back to where we were yesterday. Kind of like that. I think I had the 0 as the low and the x's yesterday. And we had this beautiful, beautiful parabola that fit right through those points. So our R-squared value was very close to 1, 0.999, blah, blah, blah. And then we took that and we said, okay, if this is what I have, and they're asking me for maximum height, I might as well just use my graphing calculator and find the maximum. But we could do it by hand by using that little x equals negative b over 2a formula, getting the 0.402 for seconds, and then plugging that back into the equation and getting 1.8 for the high. Now in this class, I think we actually got our velocity formula all done, didn't we? We just didn't have to punch it in. So we had our Vt equals, and we'd gone up and found what gravity was, and that was negative 9.352 t, and our initial velocity 3.758. So just by using the formula to get that. And then we said, well, we have to figure out when this is going to hit that CBR in order to find out what the velocity was at that time. And again, we just grabbed the calculator and said, you know what, the zero's right there. Blinky's all warmed up. So second, calculate number 2, the zeros. And Blinky's right where he needs to be. Left bound, right bound, enter. And we got 1.022 seconds. So to figure out the velocity, all we had to do was put that in for time. And, oops, not X. I'll use the fancy notation here. That velocity came out to negative 5.800 meters per second. And I think that was just the last thing that the bell kind of rang on us. So now, we just did a lot of math. I mean, there was a lot of stuff going on in this problem. And if somebody doesn't know a lot of math and they look at this, it's going to be very hard for them to figure out what's an answer here and what's not. So when that happens, we just want to write a quick sentence or two saying, okay, here's what they asked me to find, and this is what I actually had for an answer. So this said, use the models to predict the maximum height of the ball and its vertical velocity when it hits the face of the CBR. So we can just start out by saying, the maximum height of the ball was 1.8 meters. Because if you're talking to somebody, you're not going to say 1.800 meters or 1 in 800,000. You're not going to do that. So 1.8 meters. The vertical velocity of the ball when it hit the CBR was 5.8 meters per second. Now, why not put negative 5.8 meters per second? Well, they didn't really ask for direction. They asked for velocity. If this is physics, yeah, put the negative on there. In physics, they like that because they'll be able to tell you it's downward. But since we just wanted to know the velocity was 5.8 meters per second, and that would be enough. But that just pulls it all together. So when somebody's looking at our math, they're like, oh, yeah, that makes sense. They stopped there at the 5.8, so that's the 5.8 meters per second that we have for velocity. That was all we had left on that. Well, like I said, it's just kind of a strange little problem, and that working backwards from the equation kind of messes with us a little bit. And then in first hour, somebody raised their hand this morning and said, serum is one of those going to be on the test. We can't put something like that on the test. Not the whole thing. I mean, we'd have like 3 problems on our test. That would be all you would have time for. Now you got to plug in all the numbers. You have to do the quadratic regression. You have to find the max. You have to find the zero. Then you actually have to use it in the, pieces of it. Yeah, we could give you a formula and say find this, but not the whole thing. There's just too much there. It's a great problem. Don't get me wrong. It's just that we've got more stuff to test you on than just that. So we can't put something like that on there. So now, what do we need? Well, we've already had that. We need to start talking about 2, 3. That's what we need to do. Because tomorrow will be a very interesting speed teaching day. Tomorrow, because of what we have going on with the football team. In here, it's not quite as bad. And we should have a little bit of time to get through what we need. But it very well might be that I might have to record some stuff after you leave and have you finish it. We'll see how it goes.
Isn't fourth hour always the same thing for the day?
It's not exactly the same tomorrow. I don't know how they shortened it, but they shortened it a little bit. So hopefully we'll be okay. Section 2.3 is on polynomial functions of higher degree with modeling. You studied this in algebra 2. You did. When we started talking about powers, we realized that something to a degree 3, degree 5, degree 7 always had the same end behavior. And we studied that if something had squared, 4th, 6th, 8th for its degree, those had the same end behavior. And it just came down to, is it an S-curve when it's going to be an odd degree, or is it going to be parabolic when it's an even degree? So today's going to feel like a lot of review, but we've got just a couple of new things in here that I really want you to latch on to. So the review stuff, just kind of sit back and go, oh, yep, I know, I remember all that. But when I say that something's new, you might want to put a little star next to it, because that's the kind of stuff we test on, is pieces that are not necessarily all review from Algebra 2. There's something new that you have to do. So our objectives, we're going to graph polynomial functions without, and then checking with the calculator to make sure that everything's going okay. Distinguish the end behavior of polynomial functions. I know for a fact some of you were having trouble with that when we went over the 12 basic functions. So we probably won't get to that till tomorrow, but it'll be a really good review. Then we're going to find zeros of polynomial functions. We'll definitely do a little of that today. Use the intermediate value theorem. That'll be new for you. That'll be either tomorrow or after our big Thanksgiving break. And then model polynomial functions, the word problems. That we probably won't get back to until after Thanksgiving break. But that's our objectives. And what's up with that picture? Well, believe it or not, they don't want to spend thousands of dollars making a roller coaster and then put somebody on one of the cars and realize that the drop is too fast. That would be very bad. So they need mathematical models. Computers understand the language of mathematics. And they make the models, and then they put all the variables in that they could possibly have, weight of the passenger, weight of the car, all of that stuff, and run through and make sure that it's going to be safe. And it's not just for things like this. The first thing that pops into my mind when I think about this section is the fact that this country is in such dire need of new bridges. The whole country, there's bridges all over the place that are just a mess, and they're going to be gone soon. We need smart people like you to engineer those new bridges so that there aren't any issues in the future. So that is definitely something that we're looking into as we go into this section. How do you model this? How can you use that information and a little bit of engineering? So away we go. Section 2.3 says, polynomial functions of higher degree with modeling. Brief review. Graphs of polynomial functions. Degree 1 polynomial. What does it look like when you graph it? It's a line. Yep, it's a line. A degree 2 polynomial. When you graph it, what's it look like? It's a parabola. We used to have a sub that would pronounce that parabola. And the kids would just laugh. So beyond these, we have polynomial functions, obviously, of high degrees. Third power, fourth power, fifth power, etc. And they will include cubics and quartics. And that's mostly what we're going to spend our time on today. So this says, how about we just pull something out of our memories and say, here's what a cubic looks like. Well, if you're having trouble remembering what a cubic looks like, you can go back to the old-fashioned, hey, I think if I made a little table, I could start to remember what it's going to look like. So, cubics. Raising -3 to the third power, -27. I'm not going to graph that, but it tells me where to aim. -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. And even if you just did that in your head for a little bit, you go, oh yeah, now I remember. 0, 0, 1, 1, 2, 8. Oh my goodness, those lines are fading more and more as it goes on. Can't see the blue. So right there. That's our cubic. Nice little S-shaped curve there. And that hopefully brings back to you, wait a minute, but that's a positive leading coefficient. If there's a negative leading coefficient, then it's going to go that way. You start thinking about what's happening there. Because what we're trying to do is describe the and that's really what we're doing. We're saying as this goes to the left forever, this graph is going to go down. As it goes to the right forever, the graph is going to go up. So that end behavior stays consistent with any cubic that we have. Quartics. We didn't really spend a whole lot of time in now. I don't know that we graphed any quartics without the calculator in algebra 2. I don't think we did. So you just throw in some numbers. Pretty obviously, we're not going to use big numbers because look at what was happening here when we even got 3 and -3 with that one. So maybe we just go after -2, -1, 0, 1, and 2. And think about the 4 slots that would be filled because this is x to the 4th with that -2. Well, if it's 4 slots, it's always going to be positive no matter what. So that's going to be 16. This will be 1, 0, 1, 16. And of course, we're going to see that parabolic nature that any of those even degree polynomials have. And I'm not going to graph -216 and 216, but I'm going to aim for them. You know, it's telling me this is going up pretty doggone fast, almost like a vertical line. Almost. Not quite. I think I got it fat enough on one side there. There it is. So those are quartics. Now that's a quartic with a positive leading coefficient. And if we put a negative in front of it, it should be parabolic going out. So again, it's about, can we tell the end behavior just by looking at the powers? Absolutely. Absolutely. When we have the x to the 4th, as we go to the left forever, it's definitely going up to infinity. As we go to the right forever, definitely going up to infinity. And then the negative leading coefficient would be down, negative infinity for both of those. So that's a big piece of what we have to remember is just general shapes and behavior. How does all that work? A polynomial function of degree n can be written in this nasty little form right here. So, again, what are they trying to get at? What they're getting at is your highest power is going to be here. Let's say it's a 5. Then you should subtract 1 from that and be looking for a 4th, something to the 4th for your variable for the second term. And then 5 minus 2 would be 3. So really it's telling us 5, 4, 3, 2, 1 in descending order is what that's saying. And then this, a sub n minus 1, a sub n minus 2, is not really as mathematical as it is saying, here's your leading coefficient. Now, you'll have 1 in that next position that is your leading coefficient, not your leading coefficient, but a coefficient. And then you'll just continue on with those coefficients in front of those numbers. So it says a sub n is not going to equal 0, and that's because we want that first term to have the degree that we're looking for. So each monomial in that sum called a term. Now, what is special about that is the knowledge that terms are always separated by addition. So going back up here, this is a term, this is another term, that's another term, that's another term. So again, it's addition that separates these into terms. A polynomial function written in this way, with terms in descending order, that's standard form. When we talked about the standard form of a quadratic, but it could be standard form of a cubic, standard form of a quartic, standard form of a quintic. Standard form has the x's, the variables in descending order. The constants, a sub n minus 1, leading coefficient, coefficient, coefficient. Those are the coefficients of the polynomial. Where the first one, the one that's in front of that term that has the highest exponent, is called the leading coefficient. Right in the front there. And a sub 0. There's no x with it. So that is your constant. It's just a number. It's not going to change. That's why it's called a constant. Now, the nice thing about this is, if they are in standard form, we can find the y-intercept really quickly because the y-intercept is found by putting zeros in for all the x's. So that means the constant is always going to be that y-intercept, which is what's going on right here. So a sub 0 is both the initial value of the function, so if you put a 0 in, you're going to get that a sub 0, that constant, and that makes it the y-intercept of the graph. 0 what? That's a y-intercept. That's where it's crossing the y-axis. So now we're going to go back to what are a, h, and k doing, and how does that help us graph? So we're going to graph transformations of monomial functions, and it says we're going to describe how to transform the graph of an appropriate monomial function f of x equals a sub n x to the n. Oh my goodness, what does that mean? It means with the parent function. You know, talk about what's going to happen, what's your parent function, how is this going to change it if you have a number in front, numbers in back, how do we change that into the graph of a given function? Sketch the transform graph by hand and support your answer with the grapher. Just double check it. Compute the location of the y-intercept as a check on the transform graph. Yeah, if we say the y-intercept is 5, then the graphing calculator better have 0, 5 as one of its points, or we messed up. So, we'll get started. First things first, looking at this and trying to figure out, okay, what is this particular graph? And I see x cubed. That's my parent. The parent, y equals x cubed. And I just want to talk about what the numbers, what the negatives or positives are doing to change this graph. So what is this for, responsible for? Vertical stretch. So parent y equals x cubed, vertically stretched by a factor of 4. That's a good start. In fact, that's how we get the shape of our graph. We always take that along the width to get the shape. But this one has a translation also, doesn't it? Where's it going to go? Translate 1 unit to the left. Pardon me. So like I said, we go after this a little bit differently when we're graphing because we always take A along for the shape. We want a shape graph and then we want to move it to its new location. In this case, its new location is just 1 unit to the left. So we're going to graph y equals 4x cubed, dashed, dotted. And we can use what we know about cubics to do this as well. But normally we would just chuck a few little numbers in here. And we know we're supposed to get an S-curve when we get done. If we don't, we know we messed up. So negative 2 cubed would be negative 8. Negative 8 times 4 is negative 32 already. Again, I'm not going to graph that, but that tells me I've got to be pretty straight down after I get done with the negative 1. Because negative 1 cubed is negative 1 times 4 is negative 4. So that's a pretty big drop there from negative 4 to negative 32. Put a 0 in here. 0 cubed is 0 times 4 is 0. 1 cubed is 1. 1 times 4 is 4. And again, we start to see, oh yeah, there's symmetry here, so this one will be 32. Well, that's going to happen. Or you can just put it in there. 2 cubed is 8. 8 times 4 is 32. Again, not graphing the top and the bottom, but knowing I have to make this look like it's going really fairly straight up and down. So, 0, 0, -1, -4, which I hope is about there. 1, 2, 4. And then almost straight up and down. I want a little bit of that S curve in the center there. Oh, I forgot to make it dashed again because we're not done. A little bit of that off. Where's this one have to go? One to the left. Well, that wasn't all they wanted us to do. They wanted us to check it. So we plop it in our calculator and take a peek. Is that what it's supposed to look like? So I better turn my stat plots off, because that's going to be yelling at me in a minute. And we need 4 parentheses x plus 1 parentheses 2 to the third power. Zoom 6. Looks a lot like that. Well, just to be sure, they said, check out your y-intercept. 0 something. Now, we know what it's going to be because we just moved that over. But let's just say we didn't, because so some of these it's a little tougher than that. We would go back up here and we would literally put a 0 in. So 0 plus 1 is 1, 1 cubed is 1, 1 times 4 is 4, which we already knew because this one worked out a little too nice. 0, 4. So the book is saying, just so you can say, yes, I checked a point to make sure this was right. Go into your table and make sure 0, 4 is one of your points. And it was. Because it's a very nice number to work with, obviously. I don't want to put 0 into an equation. And it's a quick way to say, well, yeah, at least that point's looking good. And you can look at the end behaviors once you have a graph and make sure that matches what you know. Well, that's a cubic. We better do a quartic. By hand, we're going to graph. H of x equals negative of the quantity x minus 2 to the 4th plus 5. Okay, so I have a new parent function. This time it's y equals x to the 4th. Oh, and there's a negative out in front. What does that do? Reflect over the x-axis. So this parent reflected over the x-axis. Is that it for transformations? No. What else? 2 to the right. Translate 2 units to the right. Should I put an and? And what comes after the and? 5 units up. All right. So the shape of this one, we have to take the negative one. Whatever we have for A up here, that's going to determine the shape of the graph. If we don't put that negative on there, it's going to open in the wrong direction. So we need y equals negative x to the 4th. And again, we kind of learned our lesson that big numbers are not going to work out real well with these higher powers. So stick with the tiny ones and give yourself somewhere to aim. Negative 2 to the 4th. Negative 2 times negative 2 times negative 2 times negative 2. That's 16. But this says I have to put a negative in front of it. Because the order of operations says do the powers first, then the multiplication. Negative 1 to the 4th. Well, that's 1. But I have to slap a negative in front of that one. Always do powers first, then multiplication. This is like a negative 1 times x to the 4th. got a 0. And at this point, you might say, well, I already know what the other ones are going to be because this is symmetric. But just in case, you put your 1 in there, you get -1. You put your 2 in there, and you get a -16. Which again, we know to aim for, but not necessarily going to be on our graph. 0, 0, 1, -1, -1, -1, and almost straight up and down. And that got it all 3 times today. I have made those solid. Ugh. Like I just can't get a curve on there without drawing it solid. Done. No. We're going to move it 2 to the right and 5 up. So we'll have a new vertex at 2, 5. Use a different color. And 1 over, 1 down, 1 over, 1 down, and very, very straight looking. From there. So there's our quirk. We hope. That's why they told us to check. Say, check this thing. Let's see. Y equals. We have a negative, parentheses, x minus 2, parentheses, to the 4th plus 5. Oops, 5. I hit it. I apparently did not hit it hard enough. There. Yeah. Little skinny parabola. But just to make sure, they're saying, plug a 0 in. See what you get. 0 minus 2, -2. -2 to the 4th is 16. Times -1 will be -16. -16 plus 5 would be -11. Oh, I can't see that one. And then take a look at the table. Down at the bottom. There it is. So at least you know you've got your vertex right, and you have at least 1 point on the graph looking like it should as you go through there. So I think we did everything we were supposed to do. It didn't say anything about domain and range or any of that because we didn't done that a lot. Yeah, that's it. So now, those are too nice. Way too nice. The AH and K stuff, way too nice. Reality is they don't come prepackaged that way. They just don't. So in example 2, we see what can happen when simple monomial functions are combined to obtain polynomial functions. The resulting polynomials are not, that's a big little word right there, not mere translations of monomials. So a lot of the things that we thought we know will still hold over, but there are going to be some new pieces here when we go through these. Notice the big star has new pieces. So graphing combinations of monomial functions. Graph the polynomial function, locate its extrema and zeros, and explain how it's related to the monomials from which it is built. Oh my goodness, that's a mouthful. Well, first things first. We can see why we can't use AH and K. There's another X in that little thing. That's not been there before. That's just been 1X. So one of the things, oh, my duct tape didn't hold. One of the things that we're going to have to do is say, okay, I know what this looks like because it's an odd polynomial, and I know what that looks like because it's an odd polynomial. So when I get done, maybe it'll be odd. I better take a peek and check that out. So f of x equals x cubed plus x. Huh? Oh, I can find some easy points on this one because this is factorable. So if I make it 0, oops, too many parentheses. I got to at least figure out that it's going to cross at 0, 0, because if this is 0, the whole thing will be 0. But x squared plus 1, that's interesting. When does that equal 0? Well, if we subtract 1, oh, that's right. That's imaginary. We're not graphing imaginary stuff. We're graphing real stuff. So we're not going to be using using those zeros. But I definitely know if I put a 0 in here, I'm getting 0. So I know that's a point on my graph. That's one for us, but we've got more to do. So what we have to do, because we haven't worked with these before, is we have to make a table. I mean, we don't have any choice at this point unless we grab the calculator and just plop some numbers in. The standards so far seem to have been -2, -1, 0, 1, and 2. If we put -2 in here, we'll get -8 plus -2. That's -10. Look at these graphs and oh my goodness, now they only go out to 5. Would have been nice to have our -10 to 10 there. Put a -1 in here. -1 cubed is -1 plus -1 is -2. But there's a reason, and we'll see that later, why this is with the -5 and 5. Put a 0 in, 0 and 0 gives you 0. Put a 1 in, 1 cubed is 1 plus 1 is 2. Put a 2 in, 2 cubed is 8, 8 plus 2 is 10. So we do see the symmetry. Well, let's see what it looks like. So -1, -2, +1, +2. And then not quite as extreme as the other ones we've seen today. Oh, great, it's not going to let me erase that either. Thank you, Smartboard. Or cuss. Like that. And that is final product because we had to use a table to get that. So it says locate its extremum. This doesn't have a local min or a local max. There's no obvious hill or valley here, so we're not going to be able to do extremum. Zeros already did it right here, and in the table. We can see 0, 0. That's there. Okay. Explain how it's related to the monomials from which it was built. Monomial, monomial. Odd and odd. Give us odd. Well, the end behavior is exactly the same as it would be for x cubed. So its end behavior is matching that first variable because x to the third is definitely going to take over. If we start putting numbers in here, that's going to get big really fast. So the end behavior matches y equals x cubed. As you go to the left forever, one out forever. As you go to the right forever, up forever. So what about the other piece? It was just an x, right? Let's see. Y equals x. That is the perfect diagonal through first and third quadrant. 1, 1, 2, 2, 3, 3. Oh, hey, look at that. Look at right here and right here. It looks like it's kind of riding on that line. Y equals x. That, in fact, is what's happening. As you get closer and closer to the origin, the graph will approach y equals x. So as we move closer to the origin, the graph approaches y equals x. So the cube term, because when you put bigger numbers in there, it just gets bigger and bigger and bigger. That takes off for your that's going to be what's in charge of, okay, it's going down and it's going up. But as you get closer and closer to the origin, that second term, that little x, takes over when you're in Fractionville down there. And it will approach that line, y equals x. So, that doesn't look like much of a difference there in that problem. X cubed minus x. Let's see if it is that big of a difference. First of all, if I'm finding my zeros, I can factor twice, because that's a difference of 2 squares. Well, that means this is going to cross at 0, 0, -1, 0, and 1, 0. Cool, I already know 3 points in my table. They're going to be zeros. Put in a -2. -8 minus a -2 is -8 plus 2, which is -6. Put in a 2. 2 cubed is 8. 8 minus 2 is 6. So we're just a little bit off. Up right there. Up right there. and I start graphing it, and I, whoa, wait a minute. That means it's going to cross the x-axis. Not exactly sure how high that should be, but something's going to happen up here, and then it's going to come back, and something's going to happen here, and then it's going to take off, like that. So what that tells me is this one's going to have extra. And because we can't do that without calculus, we're going to have to use the graphing calculator. Well, we found the zeros. So your zeros were at 0, 0, negative 1, 0, and 1, 0. But we do have to grab the graphing calculator for this one so that we can find those extrema. Where is the local max and the local min? Y equals, where is it? X cubed minus x. Beautiful. Well, I went a little too high and a little too low, I believe. That looks like it's pretty teeny looking at my graphing calculator. It's not going quite that far, so I better figure out how far. Second trace, number 4, the maximum. Go to the left side of the hill, press enter. Go to the right side of the hill, press enter. Enter, yes. So we have a local max of 0.385. At x equals negative 0.577. All right. Well, that's pretty teeny. So a little more than negative halfway, 0.385. About there is about where it tops out, right there. Now I'm going to guess, because this has been symmetric up to this point, that the other one is going to go positive 5.77, negative 3.85. So let me put that on here. But that is exactly what it is. It is just a guess, and that's not good enough. So, graphing calculator, please tell me where the minimum is. I'm going to go left side, press enter, right side of the valley, press enter. Well, looky there, nice and symmetric. So, local minimum of negative 0.385 at x equals 0.577. Symmetric, linear way. Now I'm going to insert everything. Oh, we got to talk about the shape of this graph. Still is a cubic. I mean, very obviously it still is a cubic. The end behavior is definitely cubic stuff. But let's see, the second part of this would be what's going on with y equals negative x, because it was x cubed minus x. Now that's the line that goes through 1, negative 1. Oops, wrong way. Negative 1, 1. There we go. And in this one, you can see it a little bit more clear that the blue is actually right on top of that line as we go through there. So when we explain it, we're going to say the end behavior is just like the cubic. End behavior is just like y equals x cubed. But as we approach the origin, the graph approaches y equals negative x. Big numbers. Raised to the third power, going to take over those end behaviors. But fractions, the smaller numbers, that's going to be that second term that's going to take over as we look at that. So those were some really good ones with a little extra new piece. And that new piece is really talking about how do you see what's going on with the graph, knowing what you have in the equation. So on this page, we've got polynomial functions, blah, 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 for all real numbers. Hey, Hey, we already wrote that down earlier in our packet. Polynomial functions are defined and continuous for all real numbers. No breaks, no jumps, nothing weird. And why is that? Because when you go to calculus, I better spell it right here, differentiable. You want to deal with differentiable functions. That means we have to be able to differentiate them, which is a process we use in calculus. So that means no breaks, no jumps, nothing goofy, so no discontinuities. But also an introduction to one other thing that you cannot see, because we've had some graphs that did that this year. This. That is called a cusp. No cusps. Can't have anything goofy. It has to be, hey, my pencil goes all the way through this graph. So those are our polynomial functions. Now, some quick questions, because I know we're probably getting low on time, because this is about the same. Cubics. How many zeros do cubics have? Trick question. How many zeros do cubics have? 3, no matter what. Now, some of you are thinking, because I heard it, you're thinking, yeah, but sometimes we get 1 because the other 2 are imaginary. There's still 3. Still 3. 3 zeros. Graphically, we see 1 or we see 3. How many local extrema, if they have local extrema, will our cubics have? 2. Yeah, they've got to have the 2 turns to get them back on the path that they need for their end behavior. How many zeros will we find with a quartic? Yes. Not asking how many real and how many imaginary. Just how many. And then how many local extrema do quartic functions have if they have local extrema? They have to have 3. Because again, they have to get back on that end behavior path. So if they have it, they're going to have 3. And you can see that in those drawings up there, how that's going to work. So that was where I ended up with the other classes. And it's a pretty good place for us to stop too. I think that inundated your brains with all things polynomial. A lot of good stuff in there. So, we did not get to end behavior. That'll be something we kind of start with tomorrow. If you remember end behavior and the limit notation for end behavior, then feel free to go ahead. But if you're thinking, and I know this for a fact because some of you had trouble with this when we did our 12 basic functions. If you are thinking, I don't even remember how to write that limit stuff, then just don't do that until we get to that material. I would sing the whole song and say I love you tomorrow, but I don't because tomorrow is speed teaching. And I don't like speed teaching. I like speed teaching as much as you would like speed learning. It does not work out well.